case of covalent bond, it was sharing of electrons, but in the case of ionic bond, it is the transfer of electrons from one atom to another atom. The amount of energy which is required to remove this particular electron from its outermost shell is called as the ionization enthalpy. This energy that is associated by the combination of these two forms NaCl, that is called as lattice energy, which is represented by U, which is equal to minus 788 kilojoule. Hello everyone. This is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 2 of the chapter Chemical Bonding and Molecular Structure. So in last class, we discussed about chemical bond. Yes, then we studied about the Queisel-Lewis approach to chemical bonding. Then we studied about the Lewis representation of simple molecules. Yes, how to represent different molecules we studied. Right? Yes. And then about formal charge also we studied, and thereby we even discussed about the limitation of the octet rule. Right? So in today's session, we are going to discuss about ionic bond and the factors affecting the formation of ionic bond. Then we will be discussing on the different bond parameters, that is atomic radii, bond angle, bond enthalpy and bond order we will be discussing in this session. Right? So, beginning with the first one, that is ionic bond. Yes, we studied about covalent bond in detail in last session, right? So, how is covalent bond formed? By the sharing of electrons between two atoms. Right. So, what is ionic bond or how is ionic bond formed? Let's see. Bond formed by the complete transfer of one or more electrons from the outermost shell of one atom to the outermost shell of another atom, or it is the force of attraction between two oppositely charged ions. In the case of covalent bond, it was sharing of electrons, but in the case of ionic bond, it is the transfer of electrons from one atom to another atom. Right. So, one atom will be only transferring the electrons. The other atom will be only accepting the electrons. Right. So, let us take the example of sodium and chlorine itself. Right. In the formation of sodium chloride, in sodium atom, there is only one electron in the valence shell. And in chlorine, there are 7 electrons in the valence shell. So, in order to obtain the octet state, sodium atom loses 1 electron and form Na plus ion, and Cl atom gains 1 electron and forms Cl minus ion. So, what is happening here? As said, yes, the sodium atom, it has 1 extra electron in its outermost shell, or else we can say that in the outermost shell, it is having only 1 electron. So, the electronic configuration will be 281, right? In the outermost shell, there is 1 electron. Okay, so to attain octet, what it can do? Yes, lose 1 of its electron, so that in the outermost shell, only 8 electrons will be there. Now, what about chlorine? It has 7 electrons in its outermost shell. Now, if it gets 1 more electron, even chlorine can attain its octet. So, what is the best way here? Sodium can transfer 1 of its electron to chlorine, so that both of them will attain stability. Right? So, what happens when an atom loses electron? Yes, a positive charge comes there, right? So, Na, when it loses 1 electron, it becomes Na plus ion, and when chlorine accepts this 1 electron, that is gaining of electron, will result in a negative charge, right? And it forms Cl minus ion. Right? Yes. So, as now we can see that from the transfer of electrons from sodium to chlorine, what happened? Na became Na plus and Cl became Cl minus. So, there is a positive as well as negative charge here. So, a force of attraction will be there between them. So, ionic bond can also be defined as the force of attraction between two oppositely charged ions, right? Now, two oppositely charged ions are formed here. Now, the attraction between these two are called as ionic bond. So, I hope it is clear. Yes. Now, we are going to discuss about the factors, the different factors which are affecting the strength, or how the different factors will affect the formation of this ionic bond. Let's see. So, the first one is ionization enthalpy, which we have already studied in the last chapter, right? So, what is ionization enthalpy? It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Right. So, let us consider sodium itself. Yes. there is one electron in its outermost shell, right? So how do we represent it? Na and one dot, right? According to Lewis dot structure. So the amount of energy which is required to remove this particular electron from its outermost shell is called as the ionization enthalpy. Right. So whether this will be an endothermic or exothermic process. Endothermic process means energy is required to be provided. Right. Exothermic process means the reaction will result in the emission of energy. Right. So this ionization enthalpy is an endothermic process. Right. Why ionization enthalpy is an endothermic process? Yes, because to remove an electron from the outermost shell, a particular amount of energy is required to be supplied to the atom. Right. Simply it won't get removed from the outermost shell, and energy is to be given. Right. So hence it is an endothermic process. So the amount of energy required to remove this electron from the outermost shell is called as ionization enthalpy. So how does the strength or how does this ionization enthalpy depends on ionic bond, formation of ionic bond. Let's see. So lesser the ionization enthalpy, easier will be the formation of cation, which results in easily formation of the ionic bond. So what does that mean? Less ionization enthalpy. Lesser ionization enthalpy means it is very easy to remove the electron from the outermost shell, right? Yes, if it is easy to remove, that means only very little amount of energy is required. If it's very strongly bonded to the nucleus, more and more amount of energy is required to remove it. So lesser ionization enthalpy means, what does it mean? It is easy to remove the electron. No much energy is required. So that means easily cation can be formed, right? From Na plus can be easily formed because only less amount of energy is required. Right. So what happens if easily the cation is formed, easily the ionic bond also can be formed. Yes, I hope it is clear. Now moving on to the next factor, that is electron gain enthalpy. Even this we have discussed in the last chapter. So what is electron gain enthalpy? As in the name suggests, when electron is gained, yes, the energy change that is associated with it is called as electron gain enthalpy. So the energy change when a gas phase atom in its ground state gains an electron, and this process can be exothermic or endothermic. So to a valence shell, when an electron is being, or to the outermost shell, when an electron is being added, the amount of energy released or absorbed is called as electron gain enthalpy. The energy change that happens there is called as electron gain enthalpy. Right. So this can be an exothermic or endothermic process. In most of the cases, it is exothermic. That is when an electron is accepted to the outermost shell, energy is released. Okay. But in certain cases, it is endothermic process. Which cases are those? Yes, in the case of noble gases. In the case of noble gases, yes, electron gain enthalpy will be endothermic process. Why it will be endothermic? Yes, endothermic, as I said, we need to give the energy. Yes, energy needs to be supplied so that the atom will gain this electron. Right. Usually what happens? Atom will gain an electron, means it will release the energy. But in case of noble gases, we have to supply an energy so that the atom will gain electron. So why is this in the case of noble gases? What is the speciality of noble gases? We know that for noble gases, already they have attained stability. Yes, that means they have 8 electrons in its outermost shell, or they have attained octet. So, do they need to accept any more electrons? No, right? If they are stable, they do not need to undergo any chemical reactions, right? So, they are already stable. So, in such conditions, if we want to again add an electron, an extra energy is needed to be required there. Hence, in such cases, this becomes an endothermic process. I hope it is clear. Now, let's see how electron gain enthalpy is related with ionic bond. So, greater the negative electron gain enthalpy, easier will be the formation of anion, and hence easier will be the formation of ionic bond. So, what does that mean? Greater the negative electron gain enthalpy, that means more more amount of energy is released. That is, greater negative means more and more amount energy is released when the electron is being accepted. So that means easily an anion will be formed, right? So let's take the case of chlorine itself. When chlorine is accepting one electron, it becomes Cl minus, anion, right? Yes, negative charge is anion. So a high electron gain enthalpy, negative value will be there, means easily this Cl gets converted to Cl minus, and hence easily the ionic bond will be formed, right? So we can in general say that when the ionization enthalpy is low and the electron gain enthalpy is highly negative, easily ionic bond can be formed. Clear? Now there is one more factor in which that depends, that is the formation of ionic bond, that is lattice enthalpy. Now what is lattice enthalpy? This is a new term, right? So what is lattice enthalpy? It is the energy required to separate 1 mole of solid ionic compound into its gaseous constituents. So let us take the example of sodium chloride itself. Yes, it is the energy required to break sodium chloride into Na plus and Cl minus, the constituent ions. We know that sodium chloride is formed from Na plus and Cl minus ions, right? So it is the energy required to break this sodium chloride, that is 1 mole of sodium chloride, to separate 1 mole of sodium chloride into its gaseous constituents, that is Na plus Cl minus. Or we can also define as, yes, in the opposite way also we can define it. That is what is lattice enthalpy. It is the energy required to form NaCl from its gaseous constituents. From here to here as well is also called as lattice enthalpy. So I hope these 3 factors are clear for you. Right. Now we are going to study in detail about the formation of sodium chloride, which all energies are associated with it. Right. We studied about ionization enthalpy, electron gain enthalpy and lattice enthalpy. Right. So where exactly these are being used in the formation of sodium chloride, we are going to see. So this is the name that you can see, the cycle with which the sodium chloride is formed. It is called as BORN-HABER'S cycle. Yes, so let's see. It is a cycle of operations representing energy change during the formation of 1 mole of ionic crystalline solid from the required elements. So from Na plus and Cl minus, how NaCl is formed, we are going to see here. Yes, it is called as, for the formation of sodium chloride, the cycle that is followed is called as BORN-HABER'S cycle. Clear? So the first step, so as you can see, from sodium and half Cl2 combines to form NaCl. So this is the overall reaction that is going to happen here. From Na and Cl2, yes, NaCl will be formed, right? So the first step what happens here is the sublimation of sodium atom to form gaseous sodium atom, right? So sublimation, we know that. What is the sublimation process? Conversion from solid state to gaseous state directly, right? Yes, so the first step is Na solid becomes to sodium gaseous state, right? So that is the first step. Next step is dissociation of Cl2 molecule to Cl atom. Right, yes. So it was half Cl2, right, in the beginning. Yes, it was as chlorine gas it was present. Now we need it in the Cl atom form. Yes, so the dissociation is the second step. Right, now the third step is ionization of sodium. Yes, that is an electron is removed from it so that it becomes Na plus, right? So we obtained Na gas in the first step. Now this Na gas is converted to Na plus, a cation, right, by the loss of 1 electron. Now the fourth step is electron affinity of chlorine. Electron affinity, it is also called as electron gain enthalpy. Clear? Yes. So electron affinity of chlorine, the neutral gaseous Cl atom gains an electron to give Cl minus ion, and the energy released is called electron gain enthalpy, or it can also be called as electron affinity. So in this step, the Cl gas, that is the atom that is formed, is being converted to Cl minus anion by the addition of 1 electron. Clear? Yes. Now the last step is lattice enthalpy or lattice energy, that is the Na plus. See, in this step Na plus is formed, and then in this step Cl minus is formed. Now these two combine and form NaCl, right? So the Na plus and Cl minus will combine to form 1 mole of solid ionic crystals of NaCl, right? And the energy released in this process is called as lattice energy. So I told you when we were discussing about lattice enthalpy, yes, it can be either way, it can be defined. From NaCl, Na plus and Cl minus is formed, the energy associated with it, or from Na plus and Cl minus, NaCl is formed, right? Finally, we can write Na plus and Cl minus combines and forms NaCl, Right? Clear? So, sum of all these energy will be the heat of formation of sodium chloride crystal from sodium and chlorine. So, all of this energy associated from this, yes, from the first step, second step, third step, fourth and fifth step, all of this energy is associated. When we add the sum of it, finally, we can say it is the energy associated in the first reaction. So, let's see the cycle of this and we'll get a better idea about this. Okay. So, in the first step, as you can see, sodium is being sublimated into sodium gas. So, the energy associated with it, yes, the energy associated with the sublimation is 122 kilojoule. Right. Now, the next step is sodium is converted into Na plus ion, right, by the losing of one electron, which is called as ionization enthalpy, right? Yes. So, the ionization enthalpy, the energy is 496 kilojoule. We know that it is an endothermic process. That means it will always have a positive value. Now, coming to the chlorine part, yes, we can see the chlorine gas is getting converted into Cl atom, right? That was the first step in here. Yes, that is called as dissociation. The dissociation energy is 122 kilojoule, right? And from Cl gas, now it is getting converted into Cl minus ion, right? So, that is called as electron affinity or electron gain enthalpy. The energy associated is given here, that is minus 349 kilojoule. Minus, why? Because it is an exothermic process. Yes, here it is sublimation, right? Okay, right. Now, yes, from here we know that Na plus and Cl minus combines and finally forms NaCl. Right. Yes. So, this energy that is associated by the combination of these two forms NaCl, that is called as lattice energy, which is represented by U, which is equal to minus 788 kilojoule. Right. So, this is the whole of this process. So, when you add each of this energy, that is, yes, the sublimation energy plus ionization enthalpy, dissociation energy plus electron gain enthalpy or electron affinity plus lattice enthalpy. All of this added together will give you this value, that is enthalpy of formation of sodium chloride. So, this step is a sum of all of this energies that is associated. So, I hope it is clear where exactly this ionization enthalpy and electron gain enthalpy, lattice energy or enthalpy is used in this sodium, where it is associated in the formation of sodium chloride. I hope it is clear. Yes. So, this is the Born-Haber cycle. Right. Now, we are going to the next important topic, that is bond parameters. Now, what is bond parameters? Why we are studying about bond parameters? So, to understand about the different factors or different parameters which determine the stability and the strength of the bonds which are formed, we need to be required to study about the bond parameters. That is, on which parameters the strength and stability is depending. We know that ionic or covalent bonds are formed. Different types of bonds also we studied. We know that bonds are formed between different atoms, right? So, now the stability and strength of this different bonds formed, on which all parameters it is depending, we will be studying in this session. Right. So, the first factor is, or the first bond parameter is called as bond length. Yes, from the name itself, you can say it is the length between the bond or something like that, right? So, let us see the definition. It is defined as the equilibrium distance between the center of nuclei of the two bonded atoms. So, as you can see here, two atoms are bonded together. Yes, from the nucleus of the first atom to the nucleus of the second atom, the distance between them is called as the, yes, bond length. Clear? From the center of the nucleus of A atom to the center of nucleus of B atom, the equilibrium distance between them is called as bond length. Clear? Now, half of this bond length, what would you get? From here till here, what will you get? Yes, that will be the radius of the A atom, right? And from here till here, what it will be? Yes, that will be radius of B atom. Yes? Right? That is clear. Yes. Now, the bond length decreases with increase in multiplicity of bond. Now, what is multiplicity of bond? We studied about different types of bonds. Yes. Single covalent bond, double covalent bond, triple covalent bond we have studied, right? Yes. Single, double and triple bond. Yes. So, let's take the example of carbon atom. Yes. When there is a single bond and there is a double bond and there is a triple bond. Okay. So, this is how you represent single, double and triple bond. So, bond length decreases with increase in multiplicity. So, out of single, double and triple bond, triple bond will be having the least bond length. Yes, because the multiplicity is more there. Multiplicity means the number of bonds, right? So for triple bond, the bond length will be least and the highest will be for single bond, right? So single, then comes double, and then comes triple bond. Clear? So what will be the order of bond length? We are talking about bond length, right? So highest bond length will be for single and then double bond and then triple bond. As the multiplicity increases, the bond length decreases. Clear? Yes. So as I said here, from here to here, the radius we can also calculate when the bond length given. So in the last chapter also we discussed about the different radiuses which are associated based on how the atoms are bonded between each other. When they are covalently bonded, we studied that yes, the associated radius is called as covalent radius. We studied about van der Waals radius, right? So let's have a discussion on that as well. Yes. So what is covalent radius? Yes, radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. So when two atoms are covalently bonded in a bonded situation, if they are covalently bonded, yes, what did we study? Yes, it is the half of the distance between the internuclear distance between them. So as you can see here, when the two atoms are covalently bonded, yes, internuclear distance between them, the half of it if we take will give you the covalent radius. Right. Yes. Now what about van der Waals radius? It is in non-bonded situation, right? Yes. It represents the overall size of atom which includes its valence shell in a non-bonded situation. So as you can see here, when the atoms are not bonded with each other, they are not touching each other, right? In this diagram. Yes. So they are non-bonded. Yes, in a non-bonded situation, and these two will be the atoms of different molecules. Even this we studied in the last chapter. So the atoms associated with two different molecules, when they are in non-bonded situation, the internuclear distance between them, if we take the half of it, we get the van der Waals radius, right? And moving on to the last one, that is metallic radius. It is half the distance between centers of nuclei of two atoms of metal held together by metallic bond, right? So these are two atoms of metals which are bound together by a metallic bond. Right. So if we take the half of distance between the nucleus of these two metallic bonds, which are two metal atoms which are bound by metallic bond, the half of the distance will give you the metallic radius. So I hope you are clear with all the three: covalent radius, van der Waals radius and metallic radius. Now a question arises whether covalent radius or van der Waals radius is smaller, or which one is having a greater value or which one is smaller. Let's try to understand that. As you can see here, in this diagram, these two atoms are covalently bonded. Even these two atoms are covalently bonded with each other. Right. Now, what about this atom and this atom? They are not bonded with each other, right? They are atoms of two different molecules. This is one molecule, this is another molecule. So, in a molecule, when two atoms are covalently bonded, this internuclear distance, if we take half of it, yes, let's take this particular molecule, the internuclear distance between them, if we take the half of it, we get covalent radius, right? So, as you can see, the covalent radius is 99 picometer, right? Yes. Now, let's take this particular atom and this particular atom. They are non-bonded. They are atoms of two different molecules. If we take the internuclear distance of these two non-bonded atoms and take the half of it, right? So, the value is 180 picometer. So, what are we getting here? That is van der Waals radius. From this diagram itself, you can understand. Right. So, which one will be higher or which one will be smaller? Yes, the covalent radius will be smaller than van der Waals radius. Why? Because in covalent radius, they are bonded with each other. From the diagram itself, you can understand, right? So, if we are taking the distance here, it will be less. And if we are taking the distance between two different atoms in two different molecules, of course, the distance or the radius will be high, right? Yes. So, I hope it is clear. So, from this, you can conclude that always the van der Waals radius will be higher than the covalent radius. Clear? Now, moving on to the second bond parameter, that is bond angle. Yes, so it is the angle between bonds, right? So it is defined as the angle between the lines representing the orbitals containing the bonding electrons, and it is measured in degrees, right? So when we studied about chemical bonds at the beginning, I told you that they are represented by lines, but there are no lines as such present there, right? Yes, it is a force of attraction. Chemical bond is a force of attraction. So what are these lines representing then actually? Right. So the lines are representing the orbitals containing the electrons. So in the chapter structure of atom, we studied there where exactly the electrons are present. They are present inside the orbitals, right? We discussed this. So it is present inside the orbitals. So the orbitals in which these electrons are present, to represent those orbitals, these lines are made. Okay, so the lines represent the orbitals in which these electrons are present. So the angle between the lines which is representing these orbitals is the bond angle. Clear? So in this NH3 molecule, as you can see, there is an NH bond here, NH bond here, and NH bond here. So the angle between the NH and NH bond, that is the angle between the orbitals containing these electrons, is 107 degree in case of NH3. So in case of ammonia, the bond angle is 107 degree. Right. Now coming to methane, CH4, the bond angle is 109.5 degree. It is the angle between the CH bond. Clear? The CH and the CH bond, as you can see here, right? Yes. So the bond angle between the orbitals containing these electrons is given here. That is represented by these lines. Clear? Now in the case of water, it is 104.5 degree. So for ammonia, it is 107 degree. For methane, it is 109.5 degree. And for water, it is 104.5. Yes, and it gives the data regarding the shape of the molecules. That is importance of the bond angle. So if we know the bond angle, we can predict the shape of the molecules. In detail about the bond angle and the shape of the molecules, we will be studying in the upcoming sessions of this chapter itself. Right. So it also gives the data regarding the shape of the molecules. Clear? Now moving on to the third parameter, that is bond enthalpy. So what is bond enthalpy? It is the amount of energy required to break 1 mole of bonds of a particular type to separate them into its gaseous atoms. So it is the amount of energy required to break 1 mole of bonds of a particular type. That means if we want to break all the bonds in a molecule, which is single bond, right, 1 mole of single bonds present in a compound, if we have to break them, the energy associated with it or the enthalpy associated, that is the enthalpy which is required to break these bonds, it is called as bond enthalpy, right? So it is also known as bond dissociation energy, which is having a unit kilojoule per mole. Yes, it is the energy required to break the bonds in a molecule or in a compound having 1 mole. Right. So it is energy. We know that the unit of energy is kilojoule. It will be per mole. Clear? Yes. And the greater the bond multiplicity, greater the bond enthalpy. Right. So what is bond multiplicity? We already studied. Right. So let's take the same example. Yes. So out of the single bond, double bond and triple bond, which will require more bond enthalpy? Of course, it will be triple bond. Right. Yes. This carbon and that carbon, the 2 carbon atoms are triply bonded. That means more amount of energy is required to break this bond than this. So in this case, how you can say, right? Yes, that is what is written here. That is greater the bond multiplicity, greater the bond enthalpy. So that means triple bond will be having the highest bond enthalpy, then double bond, and then single bond. So I hope it is clear, right? Now moving on to, in polyatomic molecules, average bond enthalpy is used. Now what is polyatomic molecules? More than one atom is present. In this case, it is only one type of atom, carbon and carbon, which is bonded by triple or double or single bond, right? So they will have a fixed bond enthalpy. But in the case of polyatomic molecules, how do you calculate? Let's take an example and understand this. In case of water molecule, we are going to consider. Yes, we know that how we can represent water molecule. Yes, O, it is H2O, right? Yes, So in this case, you will say, what is there a difference? Here also it is OH, here also it is OH. So the bond enthalpy will be same. So what you have to understand here is the bond enthalpy required to break this particular OH bond and this particular OH bond will be different. Why is this happening? So let's say in first it was H2O molecule, right? So in the water molecule, first let me say that I am breaking this particular OH bond, right? So I am breaking this OH bond means now in that case, in this scenario, even this OH bond is present. Yes. So now what happens is a particular bond enthalpy is required. Now this bond is being dissociated. Now I'm going to break this bond, that is OH bond. So now in this case, is this OH bond present there? No, right? Only this OH bond will be present. This is already broken. Yes, only this OH will be present. So now the situation is different. So the energy required to break this OH bond will be different. So I hope you understood why there is even though both of them are OH bond, the energy associated to break them is different. I hope you understood the situation. Yes. So in the first case, water is being, yes, the water molecule is broken to HNOH first and then OH is being broken to HNO. Yes, so of course the scenario is different there, hence the bond enthalpy required to break each of the OH bonds will also be different. So the first case, the bond enthalpy is 502 kilojoule per mole, and in the second OH bond breakage it is 427 kilojoule per mole. So if I ask you what is the bond enthalpy to break all the bonds of 1 mole of water molecule, will I say this value or this value? Yes, what you have to do is in polyatomic molecules, as I said, average bond enthalpy is used. So you have to take the average of these two values. That is 502 plus 427 by 2. That is the average, right? So that will give you the bond enthalpy associated with the water molecule. Clear? Now coming on to the last one, that is bond order. It is the number of bonds between two atoms in a molecule. Yes, it is the number of bonds between two atoms in a molecule. So if let's take the same example, carbon and carbon bonded by a single bond. So what will be the bond order? Bond order will be equal to 1, right? So if carbon and carbon are bonded by double bond, the bond order will be 2, right? And if they are bonded by a triple bond, yes, bond order will be 3. Clear? So it is equal to the number of bonds present between two atoms. Yes, simple. Now, isoelectronic molecules and ions have identical bond orders. So, we have studied about isoelectronic species as well, right? So, what is isoelectronic species? The ions or atoms having same number of electrons are called as isoelectronic species. So, isoelectronic species will also be having same bond order. I hope you remember the examples that we have studied. Let's take these two. Yes, O2 minus and F minus. We know that in both these cases, a total of 10 electrons will be present, right? Yes, so in these cases, right, in isoelectronic species, the bond orders will be same. So what is bond order? It is the number of bonds present between two atoms. Clear? So for example, in hydrogen, that is H2 with a single shared pair of electron, right? H single bond H it will be. So it is having a bond order 1, right? In the case of O2, oxygen, it is bonded by a double bond. So the bond order will be 2. And in the case of nitrogen, how they are bonded? By a triple bond. So the bond order will be 3. So I hope it is clear. Right. Now let's all together see how these three will change with each other, right? If bond order is increasing, what happens to the bond enthalpy? What happens to the bond health? Let us summarize this. We have already studied this, right? So let us say if the bond order is increasing, that means if from 1 to 2 to 3 it is increasing. So if bond order is increasing, that means what happens to the bond enthalpy? Bond enthalpy also increases, right? What did we study? For triple bond, yes, the highest enthalpy is required, right? So, from 1 to 2 to 3, if the bond order is increasing, that means bond enthalpy is also correspondingly increasing, right? Now, what about the bond length? Yes, if bond order increasing means from 1 to 2 to 3, if it is increasing, what is happening to bond length? Bond length will decrease, right? Yes, also if bond enthalpy is increasing, that means bond length will be decreasing, right? So I hope the relation between these three is clear for you. When bond order is increasing, correspondingly bond enthalpy will also decrease, and they are inversely proportional to bond length. Yes, if the bond length for a single bond I am considering, we know that the highest bond length is for single bond. So the bond enthalpy will be least in that case, and even the bond order will be just 1. So this is the relation between them. When bond order increases, bond enthalpy increases and bond length decreases. So how the different bond parameters are interlinked with each other. So in the next session, we will be discussing on bond polarity, dipole moment, and then we will be discussing on Fajan's rule. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.